Okay, so the derivative can always be considered as a rate of change of one variable or one quantity with respect to another. Now, we haven't really talked about it that way very much, but we're going to come up to some applications here of differentiation pretty soon where this is going to be our focus. It's going to be on relating different rates of change. Okay, in that case, that's all. Then we were just totally focusing on the rate of change aspect of the derivative. Whenever you're doing calculus, it's helpful to always think about things in terms of what a graph might look like. So even if there's not an obvious graph presented to you in a question, you want to think about, okay, so if I were to graph the dependent variable on the vertical axis and the independent variable on the horizontal axis, what would this graph look like? And then that helps me think about calculus too, because we know that the derivative is just the slope of the function, right? So it's always good to kind of try to think about things in terms of what they would look like if I graphed them in a coordinate plane. Okay, so what do we mean by this using talking about a derivative as a rate of change? Well, what about the forms that we already know? We know we could write a derivative as dy dx. Well, how would we say that then? Dy dx, we would literally say is the rate of change of y with respect to x. That's what that means, right? What about f prime of x? Well, that's the rate of change of f of x with respect to x. Or we could say the rate of change of f with respect to x, okay? And what about y prime? Well, y prime would be the rate of change of y with respect to whatever the independent variable is, probably x. So once again, that would be the rate of change of y with respect to x, okay? Let's look at a couple more specific examples. These are just general kind of mathematical derivatives, but mostly like in physics, for example, we're using derivatives to represent the rates of change of specific quantities, right? The interesting quantities to us. Like maybe if V of R represents volume as a function of radius, then somebody tell me, what would V prime of R, how would I say that? If V of R represents volume as a function of radius, Isaac, what does V prime of R mean then?
Not sure.
Okay, somebody help Isaac. Julia, help Isaac out here. If we want to say it as a rate of change.
I'm not sure either.
Okay, let's go back and look at these examples up here again for just a second more. So if I've got something like dy dx, that's the rate of change of y with respect to x. We're looking at how much is the y variable changing compared to the change in the x variable. F prime of x would be the rate of change of f with respect to x. So if we have v of r, what would v prime of r mean? If v represents volume and r represents radius, what's v prime of r going to be, do you think? Somebody chime in if they think they got an answer on this one. There it is. The rate of change of volume with respect to radius. Okay, what about if S of t represents position as a function of time? Then what is S prime of t going to mean? That's a derivative. If I express that as a rate, what's that going to mean? Somebody different, jump in.
The rate of change of position with respect to time.
There you go. And then what about this bottom one? If T of M represents the average water temperature as a function of month, then T prime of M represents what? The rate of change of what?
Water temperature as respect to time, or month is the unit of time.
Okay, so the rate of change of water temperature with respect to month. Okay? We good? Everybody get that? So how about if we look at a couple examples then? And you're going to look at some stuff like this on your next homework. I'm going to have you're going to have to look at some physical situations where you're given some functions and you've got to calculate and interpret what the derivatives mean as rates of change. So here we've got in this equation, R of V equals 5,400 divided by V can be used to determine the heart rate R of a person whose heart pumps 5,400 milliliters of blood per minute and V milliliters of blood per beat. Okay, that's a lot to wrap your mind around here, but this is actually a real thing too. This is a real model that people use in health profession. So think what that means then. This is going to predict the output is going to be the heart rate if a person is pumping blood at a rate of 5,400 milliliters of blood per minute, but the V stands for the volume of blood per beat. Then what does it mean if we're going to calculate R prime of V? What is that? Well, that's the rate of change of the output variable. It's a pretty easy formula, isn't it? When you guys you got the hang of this on that last page, when you're writing these as rates, it's always going to be the rate of change of the dependent variable or the output variable with respect to the independent variable or the input variable, right? Every time. That's the recipe for expressing a derivative as a rate. So here it's going to be the rate of change of the output variable R, which is heart rate, with respect to the input variable, which is the output per beat, right? The volume of blood per beat. Okay, let's do this one. How could I do this derivative? We got to think back to what we looked at a couple days ago, right? Our generalized power rule. R of V equals 5,400 divided by V. That does not look like one of our rules, does it? It doesn't look like one of our rules at all. That looks like some kind of a quotient. I haven't given you any quotient rules. Maybe I made a mistake. Is this fair game? Can you think of a way to rewrite this thing? Andy, can you think of a way to rewrite this so I could use the power rule here?
I'm not quite sure.
Okay, if I've got 5,400 over V. Now, the only way I would know how to do this is if I had V to some power, right?
Yeah.
So how could I write V to a power there?
Maybe like -1 or something.
There you go.
Yeah.
5,400 V to the -1. Now all of a sudden that looks like something we can handle, doesn't it? Right? That looks like an application of the general power rule. So Daisy, if I apply the power rule here, it's been a while since we did the power rule. How about if we let's write it down real quick, just so we can remember what it is. We said the derivative with respect to x of x to the n. Daisy, what did that equal? You remember? What did we do? Like if we're taking the derivative of x cubed, what would you do?
Wasn't it like n times x to the n minus 1?
That's exactly what it is. N times x to the n minus 1. Okay, so let's apply that here to this problem. So if I want to calculate r prime, what am I going to get?
Negative 5,400 v to the -2.
There you go. We're going to bring the exponent down front and multiply it by the constant, right? And then we subtract 1 from the exponent. And so we get that, don't we? V to the -2, after all, is just 1 over v squared, right? So there's our derivative function. Okay, that's useful, right? This is telling us the rate of change. Now, and it's really hard when you first start thinking about this stuff in a calculus class. It's very difficult to interpret what this means, I think. It's just not normal. You haven't done anything like this before. So what does this really represent, this rate of change? That's saying that this is how fast, the rate at which our heart rate is going to change with respect to the volume per beat for a specific value of V, right? See what I'm saying? The rate at which your heart rate is impacted by changing the volume per beat is going to be different at different parts of this curve. This rate versus V curve up here, right? Sometimes it's going to have a bigger impact than at other times, and we'll look at some more examples of this. So then, how about this? Find the heart rate that would be predicted by a beat output of 60 milliliters per beat. How would I find that for part B? What do you think? What would I do there? Andrew? Okay, if I want to know what is the heart rate that's predicted for a volume per beat of 60 milliliters per beat, where would I go to find that? I've only got two functions on the page here. I've got this function and I've got the derivative function. Which one of those is outputting heart rate? The original one, right. Okay. So then what would I do? If I want to, this is just a value of V, isn't it? Yeah, just plug in 60 in, aren't I, into my function. So 5,400 divided by 60, that's just 90, right? So I should expect, based on this model, that, typically a heart rate should be about 90 in that situation. Okay, what about part C? Find the rate of change of the heart rate when the output per beat is 60 milliliters. Let's see here. Kirsten, what am I going to do for that one? Down here. For part C.
Don't you plug it into the second equation?
I do. I'm plugging it into the derivative, don't I? Right? Because now we're trying to evaluate the rate of change for a specific input, aren't we? Right? So we'd plug that into the second function, and we would get a value of negative 1.5. Now, what would the units of that be? Let's think about that in terms of units. R prime of V, that's going to be the rate of change of the heart rate with respect to volume per beat, right? So the units then of that would have to be in terms of the units of rate divided by the units of volume per beat. Well, the units of heart rate are beats per minute, right? So that's what's going to be on the top of if I want to write this maybe using a fraction bar, it's a little easier to see what's going on. So R prime of V is going to equal some number that we could calculate, but the units will always be units of R, beats per minute, divided by units of V. Well, the units of V, we're measuring that in milliliters, right? So those should be the units of the derivative. Sometimes it's easier to think about that if I write my derivative, or at least if I think about it in the quotient form instead of the prime form. R prime of V is the same thing as dr dv. Rate of change of radius rate of change of heart rate with respect to volume per beat, right? And so I've got units of R over units of V. Okay? Give me a 1 to 5. Give me a 1 to 5. Okay. You type it in chat if you're not showing me fingers. I want to see where we are on this. Okay. So now try to interpret this then. That means that when the volume per beat is 60 milliliters per beat, if I change that slightly, that's going to have this kind of an impact on my heart rate, right? This is how fast the heart rate is changing in response to a change in the volume per beat. Okay, it kind of tells us how sensitive is the output to the input, changing the output to a change in the input. Okay. Let's try another one. Okay, based on the data from a research group, a model for the total stopping distance of a moving car in terms of its speed is this right here. Here's my function. So we should really write that as S of V, right? Because the output is stopping distance S and the input is the velocity or the speed V. Okay, where S is measured in feet and V is measured in miles per hour. The linear term, the 1.4 V, they tell us models the distance the car travels during the time the driver perceives a need to stop until the time hits the brake. So I guess that must be something like 1.4 seconds on average. And the quadratic term models the additional braking distance once they are applied. Okay, so what if we want to find ds dv? Now, somebody tell me, what does that say that? What is that as a rate? How would I say that, Lily? What is ds dv? The rate of change of what with respect to what?
Is it the rate of change of feet in respect to miles per hour?
Okay, good. So that's fine to do. You're thinking about the units, right? And that's a good way to think about it. But if we wanted to really name those quantities, the feet is really, that's the unit we're using to measure stopping distance, right? See what I'm saying? And the miles per hour is the unit that we're using to measure speed, right? So really, we probably want to tweak that just a little bit and say the rate of change of stopping distance, and you could add stopping distance in feet with respect to speed in miles per hour. Does that make sense? Okay. So let's do some calculations here. At 55 miles per hour, well, let's make it, first we have to calculate dsdv, don't we? Okay, so we haven't done that yet. Let's calculate dsdv. Here's the function s. So then what is ds dv going to be? Now I've got a sum of two terms, but that's no big deal. We just differentiate term by term, right? So Amber, what are we going to get if we take the derivative of this function right here with respect to v? What do I get from the first term?
Um, 1.4.
That's it, 1.4. Good. 1.4 plus, what about the second term? How am I going to do the second term?
The nx to the n minus 1.
There you go. Good. So in this case, it's a v. So I'd bring that 2 down front, and I'm going to get, what, 0.108 v. Is that right, everybody? Did I do that right? I think I did. So there's my derivative function. So if I evaluate this at 55, what do we get? What do we get here? Somebody plug that in your calculator. You get something like that? That looks about right, doesn't it? Let's see, if I'm plugging in 55, I'm getting about 1/10 of, just a little over a tenth of 55 is going to be, like 6-ish, something like that, right? And then a little less than that, and then plus 1.4. Yeah, that seems about right. And look at the units. Feet per miles per hour. Okay. What if we plugged in a 75? If we evaluate the derivative at 75? Well, that's going to give us what? 1.4, just a little over almost 1.1 times 75. So that's going to be like what? 7 point, like 8.2-ish, something like that, plus 1.4. A little off, but you get the idea, about 9.5, right? Okay. Interpret that. Okay. Why is it important not to go too fast? I mean, what's happening to your stopping distance here? The stopping distance actually is quadratic, but the other thing that there's another part of this, right? We could say it's probably more dramatic just to plug values into the stopping distance formula, right? Somebody do that real quick. What do I get if I plug in? What do I get if I plug in 55? What's S of 55? If I plug into my original function. Somebody got a calculator handy, crank that out. And somebody else crank out S of 75. You got an answer? Speak up when you got an answer. Okay, so 240.35 for the first one. How about the second one?
And for 75, it's 408.7.
Okay, well, there's a couple reasons why you don't want to drive a car too fast. One of them is because look at that. Even though you only increased your what is 75 divided by 55 real quick? It's a decimal. Okay, what is 408.7 divided by 240.35? Okay, so even though you only increased your speed by 36%, you increased the stopping distance went up by 70%, right? So it's nonlinear, and we can see that because there's a v squared there, right? So, and there's, and maybe if we have time, I'll tell you the physics behind that, but not today. There's another part of this, though. How about when we evaluated the derivatives? What's this telling us? At 55 miles per hour, how do we interpret this stuff? And let's look at what their answers are. What's the best choice here? What is the derivative telling us? A, B, C, or D? What do you think? Let's take a vote on this. Let's take a vote. Everybody, A is 1, B is 2, C is 3, D is 4. So either type it in chat or just flip your camera on and let's take a vote here. What do you think? One, two, three, or 4? Okay, I'm seeing lots of 2s. That's the right answer, but I don't really like it very well. I don't really like that as the answer. That's what the book says the answer should be. And it's not bad. I mean, it's okay. It's roughly what it means, but not exactly. And we want to articulate why that's really not great. Well, actually, I won't waste time on that. I'll just tell you. The derivative represents the additional number of feet needed to stop a car for a 1 mile per hour increase in the speed. I mean, kind of. But if I were actually to change the speed by 1 mile per hour, wouldn't that also change the derivative a little bit? Would change the output? You get that? So it's kind of like if you think about this in relation to what a speedometer is telling you when you drive a car. If you're driving a car and the speedometer says 60 miles per hour, does that necessarily mean that you're going to travel 60 miles in the next hour? No, it doesn't, right? That's an instantaneous rate. Agreed? So it gives you an idea, based on we know we're comfortable with the idea of what a mile per hour means, what 60 miles per hour means. We know what an average speed is. That's telling us at that moment, that's exactly the rate we're traveling. If we held it right there, that's how long we could travel 60 miles in 1 hour. But that's just at that one moment, right? Well, the same thing is going on here. At 55 miles per hour, that's telling us that if we were to tweak this a little bit, if I were to change my speed, this is the rate at which the stopping distance is going to increase at that speed. It's going to increase at a rate of 7.34 feet per mile per hour, right? Whereas if I am going 75 miles per hour, any change in speed is going to have a bigger impact on my stopping distance. Okay, there's the double whammy. Not only is your stopping distance increasing disproportionately, but the rate at which your stopping distance is changing is higher at 75 miles per hour than it is at 55 miles per hour. Okay, here's maybe even, I think those are a little harder to get at because they're sort of, they're valuable functions, but they're not very visual. You can't really stare at this and think about it. But here's one you can. Okay, we've probably all had this experience. If you're blowing up a balloon for a kid's birthday party or something like that, initially it's pretty satisfying, right? The first couple breaths you take into the balloon, the thing just blows up mightily, right? And you think, oh, this is going to be a piece of cake. This thing's going to blow up so fast. But then after a while, it's not so fun because after a while, each time you take a big breath and you blow it into the balloon, you hardly even see any difference, right? I mean, give me a thumbs up if you can relate to that, if you've ever had that experience, right? Blowing up a balloon. Well, you've probably wondered why. And that's, in my effort to make math topical for you, I want to be able to explain that to you. That's what calculus is all about, is explaining things like that. So if we have the volume function, V of r equals 4/3 pi r cubed, right? There's volume as a function of radius. Well, let's calculate dV dr, or V prime of r, whatever you want to call it. Let's call it dV dr right now, just so we can emphasize the fact that this is a rate. What is that? What's that give us, Natalie? If I differentiate that, what do I get? Questions? Oh, no, yeah, questions for Natalie. Did she answer there? Oh, okay. Mike isn't working. Gotcha. Madeline, help her out.
Wouldn't it just be 4/3 and then 3 times pi r squared?
There you go. And 4/3 times 3 is just 4, right? The 1/3 would cancel with the 3, so I get 4 pi r squared. Okay. So the rate of change of volume with respect to radius is 4 pi r squared. Well, what does that mean? The rate at which the volume is changing when I increase the radius by a certain amount is going to increase as the radius increases. So in other words, if the balloon had a radius of 1 compared to a radius of 10, when the balloon has a radius of 10, any change in the radius is going to create a bigger change in the volume, right? That makes sense. Well, what if we flip this around? This is really the reciprocal of the rate we're interested in if we're looking at the situation up here in red. So what we really want is something like this. dr dv. Because every time we blow a breath of air into the balloon, we're giving it a little piece of volume, right? We're changing the volume a little bit. We want to know, how is the radius responding to that? Well, this is kind of something cool that we can do here. If dV dr equals 4 pi r squared, then dr dV is just the reciprocal of that. So I get 1 over 4 pi r squared. Now look what's happening there. As the radius increases, that's making this fraction smaller and smaller, isn't it? Well, what is this? dr dV. How would I say that as a rate? That's going to be the rate of change of radius with respect to volume. That's what we're interested in. As we're adding pieces of volume in this, how fast is the radius changing? What's the rate of change of the radius? The bigger the radius is, the smaller the rate of change of the radius every time we put a breath into the balloon. Let's look at this graphically. So here's V of R, right? And that makes sense, right? That's just that's 4/3 pi r cubed. It's gonna go up as a power function as r cubed goes up pretty fast. If I look at the rate of change, if I look at V prime of R, man, it's even steeper, right? The further we go out to the right, the bigger the value of R, the faster the rate of change is going to be, okay? But what we want to do is we want to look at this backwards. We want to look at radius as a function of volume. So let's do that. So if I input a certain volume, then what's the radius of the balloon going to be, right? So when the volume is 4, the radius is about 1. When the volume is 6, it's just a little bit bigger than 1, okay? If I take that derivative, if I take r prime of v, which is what we just talked about a second ago, look at that. Look what's happening here. It starts off being really big, right? Starts off being really big. The rate of change of radius with respect to volume is huge, which means that when you put those first breaths in, you're seeing a really rapid increase in radius. But as you move out there a little further, as R increases, look what happens to that rate of change. It gets really small. That's why this gets so tiring, why it's just not very, after a while, it's not very fun. Because now as you're blowing air into the balloon, the radius is not responding very quickly. It's not changing much, okay? Give me a 1 to 5. Do you see what I'm saying by like how the derivative represents a rate of change there? That I think is a pretty good model to use to think about the concept. Okay. All right. We'll go back to that again and again throughout the year. We're going to talk about rates of change all the time, and we'll get into some really cool. We need a little more calculus to get into some really cool ones like kinematic stuff, but we'll get there soon. So we'll come back to that. Derivative rules. I'm just going to give you some. How are we doing for time? 10:45. Nope. 11:40. Okay, we're not bad. So we already know some stuff, right? We already know we know that the derivative of a constant is 0. We've talked about that. We know that the derivative with respect to x of a sum or a difference of functions is just the sum or the difference of the derivatives. We just differentiate term by term. We know the generalized power rule, but here's 3 more I'm going to give you. The derivative with respect to x of sine x is equal to cosine x. Whoops, that's a mistake. There's supposed to be a minus sign there. I got to fix that. There should be a minus sign in front of that one. It's minus sine x. And the derivative with respect to x of e to the x is bizarrely e to the x. How about that? The exponential function, that's pretty crazy. The rate of change of an exponential function is equal to the value of the exponential function all the time. That's crazy, right? And we'll focus on the calculus of exponential functions a little bit later on in the class. We'll look at some really cool applications of that. But we can just add these to our tool belt. We'll just practice using these. I don't want to get too bogged down in this stuff, but I do want to show you guys some proofs here too. I don't want to go through a ton, but I want to go through some. And this seems like a pretty good one. Let's do the sine one real quick. And I'm just going to, normally if we met every day, I would let you guys kind of help me out with this, but I'm just going to plow through it. And you just try to follow along and ask questions if you need to. Well, first of all, what I want to illustrate by this is if I want to come up with a new derivative formula, I've got to go back to basics and I have to start from scratch, which is always my limit definition of a derivative. So it is important, right? When we're doing proofs, we're starting with the limit definition of a derivative. So this would look like the limit of sine of x plus h, right? F of x plus h minus f of x over h as h approaches 0, right? And then all we have to do here, this is not a really very hard one. We're just going to have to expand this sign of a sum, right? And so that's going to give us the limit of the sine of x plus h. That would be, let's see, that's going to be sine plus sine cosine. So that's going to be sine x cosine h plus sine h cosine x, and then we got our minus sine x over here, all over h. Well, here's the way. I haven't done this one in a long time, but I can tell you, I mean, you kind of know how this is going to work out here. Here, when I'm doing this problem, this is what I'm thinking about. I'm thinking that I've got sines and cosines in here, and that as h goes to 0, that's the variable of our limit. So I want to somehow extract from this our special trig limits that we know. And there's only 2 of them that we know, and we only use one of them really very often, but there's 2 that we know. You fill in the blank here. The limit of sine theta over theta as theta approaches 0 is what? Everybody? It's 1. Good. Okay. What's the other one we know in terms of cosine? You remember the limit of 1. This is the one we don't use very often. You probably don't have it memorized yet, but you need to. This is one you're going to use it all year. Remember, this is the one, the limit of 1 minus cosine theta over theta as theta approaches 0. What's that one equal? 0. There you go. Good. So that one's 0. So those are our 2 special trig limits. We want to have those pop out of this, right? Well, how could we do that? If we look up here, we see that, well, there's a sine h and there's an h. So this term right here, there's one limit we could get out of this, right? So we could write this as the limit of, let's put this term first, sine h over h times cosine x. And then let's put these terms second. Well, if we want to get something like this coming out of it, right? So if we're going to look at these 2 terms, the green terms are going to be the second 2. What could I do? Well, if I factored a sine x out of both of those, I would have a cosine h minus 1. That's close. I just want the opposite of that, right? So let's factor out a negative sine x. So I get minus sine x times what's left over. If I factor out a minus sine x, I get a 1 minus cosine h. And let's go ahead and group the h there, right? Because I've got a common denominator here, I'm just splitting that up into each of these 2 parts, right? Everybody see that? I'm just splitting the common denominator. And technically, I really should write the limit down twice even here because I'm taking 2 separate limits. When I take these limits, as h approaches 0, this limit is going to 1 and that limit is going to 0, right? And so we get our answer then. We get the limit, when we take our limit, we just get a cosine x minus 0. So there's our answer. The derivative of sine x equals cosine x, right? And we could do the same thing for, we could just as easily show if we took the derivative of cosine x, we could show that we get negative sine x, okay? All right, so let's just practice a little bit. We've got those 3 standard forms. If f of x, and these are really simple problems, we'll go through these in about 5 seconds here. F of x equals 3 e to the x. What's f prime of x? The 3 stays out front. That's a constant. You remember what's the derivative of e to the x? E to the x. I see people saying it. Yeah, e to the x. So the answer is just 3 e to the x. Okay. How about this guy right here? The derivative of x squared plus e to the x. Well, we just differentiate term by term. What's the derivative of x squared? We agree that's just 2x, right? Plus the derivative of e to the x is e to the x. Okay, how about this one? The derivative of sine x is cosine x minus the derivative of e to the x is e to the x. Done. These are my derivatives, right? I should have written out, this is f prime of x, and this is f prime of x. So those are super easy to use, no big deal. We just added a few more basic derivatives to our toolkit. Okay, but what happens when we run into a situation like this? Find the derivative of h of x, which is a product of these two functions. We could do this one now. We could do this by just expanding out this product and then differentiating term by term using the power rule. I would just get a polynomial if I expanded that one out, but that's kind of a lot of work. Okay, so you could say, well, we don't really need this product rule thing, but what about one like this? We can't do this one. We have to know how to take the derivative of a product, and it is not just the derivative of the first times the derivative of the second. That's not the rule. Okay, we have to come up with a product rule. Do we have time? Okay, I'm gonna crank through I won't do the quotient rule, but I'm just gonna do the product rule. I want to show you how you could do this one. So if we want to prove the product rule, we want to know what is the derivative. If let's say h of x is equal to the product, we'll do it this way, of f of x and g of x. If I want to calculate h prime of x, I'm just going to go back and use my limit definition again, right? H prime of x is going to be the limit of h of, I'll use delta x because I had an h in there. That was a bad call on my part. It's going to be the limit of h of x plus delta x minus h of x over delta x as delta x goes to 0, right? Okay. Well, what's h of x plus delta x? If h of x is f of x times g of x, isn't that just going to be f of x plus delta x times g of x plus delta x minus f of x times g of x, all divided by delta x? It's the limit of that, right? As delta x goes to 0. Okay, why did I leave that big space? The reason I kind of wanted to show you this one is because what I remember about this, I have to think about just for a second here about what the specifics are, but this is going to be one where instead of multiplying by 1, we're going to add 0, which is the other identity, right? Most of the time when we're doing proofs, we end up multiplying by 1 in some tricky form, right? Because we can multiply by 1 and that's the multiplicative identity, and it doesn't change the value of what we're multiplying by 1. Well, the additive identity is 0. So I could do something like this. I could do something like I could subtract, I guess it doesn't matter, f of x plus delta x times g of delta x, and then turn around and add that term. G of, I want to do, you think for just a second here. I think I just want to do a g of x there, don't I? Yeah, that's not g of delta x, it's just g of x. Yeah, I had to think there for a second, but that's just going to be a g of x. Okay, I've added 0, right? I've added the same term that I've subtracted, but we're just going to group this thing in such a way that this will be helpful. So let's take these first two terms right here, and let's factor out an f of x plus delta x. So if I factor out f of x plus delta x, what am I left behind with? I'm left behind with g of x plus delta x minus g of x. And let's group the delta x in the denominator with that stuff, right? What are we left behind with then? So let's group these together right here. And if I factor out a g of x, what am I left with? Then I'm left with f of x plus delta x minus f of x over delta x. And if I'm taking that whole limit as delta x goes to 0, do you see anything tricky going on there? What is that right there? What is the limit of g of x plus delta x, that's supposed to be a delta x, minus g of x over delta x as delta x goes to 0? Anybody recognize what that is?
That's just the derivative of g of x, right?
Yeah, that's this whole thing right here. In the limit, right, is just g prime of x. Okay, what is this right here? What's the limit? I'm taking a limit of all this stuff, right? What's the limit of f of x plus delta x minus f of x over delta x as delta x goes to 0? Well, that whole thing is just f prime of x. So what do we get then? Well, we got h prime of x equals, if I take my limit now, right? If I take my limit as delta x goes to 0, that becomes just plain old f of x plus 0. So f of x, this we already said becomes g prime of x plus g of x times, we said in the limit, that becomes f prime of x. Look at that. That's our product rule. How about that? If I take the derivative of the product of f of x times g of x, I get f of x times g prime of x plus g of x times f prime of x. Okay, so that's the product rule, right? There it is. Derivative of the product is equal to f of x times g prime of x plus g of x times f prime of x. And it doesn't make any difference which one. No, these are interchangeable because it's a sum. And we know that we can commute the terms in a sum and it's still equal, right? Commutative property of addition. An easier way to say this one, and here's how we'll always talk about it from now on. This is too much to write and too much to say. F of g of x times g prime of x, you just get tired saying that stuff. So let's make a little substitution here. Let's just think of u as being the first function, call it f of x, and v as being the second function, call it g of x. Then the derivative of u times v is just u v prime plus v u prime, right? Okay, and we could extend this. I don't want to do the proof, but it would just be more of the same stuff. We could extend this thing, and we could have as many factors in the product as we want to. If we take the derivative of u times v times w, well, then you see what the pattern is. It's going to be u times v times w prime plus u times v prime times w plus u prime times v times w. So we get as many terms as there are factors in the product. And with each term, one of those factors gets to be a prime, right? Okay, that's a lot of stuff. I really wanted to get through some examples, but that was probably a little bit ambitious today with all that rate stuff. So I'll put an assignment up. We'll finish going through. You can get started on it if you want to. A lot of it you could do right now. Some of it, like the rate stuff for sure. Some of it's going to be a little bit challenging because we haven't talked about quotient rule stuff yet. But if you want to get a jump on it, you can. We'll finish it up on Tuesday, right? Yeah, finish it up on Tuesday and maybe add a little bit more. Okay? Drop in if you have questions. Have a great weekend. Think about calculus a whole bunch, about balloons. Hope maybe you'll blow up some balloons. I don't know. See you later. Have a good one.